that nice sunrise color. Why is it orange today? Yesterday it was like purple.
I'm going through the rainbow.
Well, in other classes, they use a true display, meaning display, and then there is a source that reflects the face. Then the quality is better. And here it's the same, like projector is source of light, and therefore it interferes with lamps. And you all who will stand here will look. So,
Oh.
Can you please also project the camera onto back screen? And keep the computer cameras here. Okay, excellent. Thank you so much. Well, many thanks for coming. So today will be a special meeting because the lecture will be presented by attendees of the class. So here are your notes, and now you see why I was asking you to prepare them a little bit ahead of time and send them by midnight. So it takes a little time to look through,
I forgot to put your name on it.
make objections to you if something is wrong, and to print ahead of time. So if you would be sending it like 5 minutes before the start, it would be too late. So, who we are, what are we doing, and what is our goal? So, it is a physical chemistry class that it is based in on the based on what? On quantum theory. That is one of the counterintuitive theories that contradicts with common sense. Therefore, we do a slow start and do it not immediately, but slowly but surely. So we have practiced slow start for about 6 meetings, and now we summarize this slow start with presentations of the summary of the background of quantum theory, which is known as postulates. We do have 7 groups presenting, 7 mini teams presenting on the subjects about postulate, about wavefunction, about observables, about measurement, expectation values, and how observer changes the system. What is time dependence? This was main focus on our lectures. And then there will be another team that will provide a little bit of additional mathematical background that we will use in the rest of the course. So it is supposed that each of us, including me, speaks no more than 5 minutes plus questions, ideally 3 minutes, and then everyone is invited to ask questions to the presenters. This material will not be covered in the rest of the class, so if something is not clear, take your chance and ask the presenters. The idea is one person becomes an expert in one subject, another person in another subject, and then we exchange our expertise through this verbal interaction as much as it is possible. So, practically, how do we arrange it? So, there is a computer with standard mouse, keyboard, and touch screen. So your presentations are on the desktop, 1, 2, 3, 4, 5, 6, 7. And if you hate numbers, there are names. So you recognize you or your partner. So you click, it comes up, And then there is a symbol to start presentation. If you are not a PC person and you prefer Mac or Linux, so this is a symbol to start. So with this, I would like to invite first two speakers, Hanna, Fanouz, and Breuer, to present their subject on postulate number 1. Okay, I start the stopwatch. And you can see on the back screen if you are in the focus of the camera. Whenever you want to be in the focus or avoid it.
Set. All right, no golf clap when we came up. My name is Austin, and so our postulate is quantum mechanics postulate number 1. And just stating kind of the main goal of this postulate, since this class is all about goals, what we're looking at is just basically trying to prove that something exists in space and time. And for us, that's going to be that electron or that wave formula or wave particle that's in that in space and time. So that's essentially what the definition of postulate 1 says. It's the complex wave function multiplied by the wave function itself comes to give us this determination that there is a particle at some space and some time dictated by dx, xo, and t0. It works with any variable, so if you were to take all space and time, dx, dy, dz, take the integral of both the wave functions, you're able to find that the probability that there's some kind of particle or wave function in this space is going to be exactly equal to 1. Essentially, giving a really common example, if I'm standing in this room, there's a 100% possibility that I'm standing in this room. Exact same thing, there's a 100% possibility that there's an electron somewhere in space and time. What this really kind of comes down to and why it's important to quantum mechanics is that we get these observables that we can get from that. Since I'm standing in the room and there's some existence of me in the room, you can take things such as my height, my weight, things like that. In the same sense that you can do that for quantum particles or wave functions, you can take the observables from them and figure out what you need to, such as momentum, angular velocity, things like that, and get those observables to dictate other equations, which the mathematics is what Hanna will take us into right now.
He kind of touched on this a little bit, but normalization is kind of the scaling of the wave function so that the probability over all space is equal to 1. And then so you see the integral of the complex conjugate of the wave function times the wave function dx is equal to 1. And then that's kind of saying the same thing as the magnitude squared is equal to 1. And these are just the conditions for that probability function to work. And so it has to be a single valued function. So for each position in space, the x, there's only one position in time, t associated with it. So like this graph of the wave function would be a single valued function. And also the second derivative of the wave function must exist to set up the Schrodinger equation. And also for this probability function to work, the function must be continuous, meaning f of x is defined at a, the limit of f of x as x approaches a exists, and the limit of f of x equals f of a. Yeah.
So it's really, no, go ahead and summarize it here quickly if you want.
Okay, so kind of the summary for all of this is it allows further postulates to be developed because it gives support that the particle or wave function exists somewhere in space and time. This gives us as chemists the possibility to find observable measurements in quantum mechanics. Can I do last two? Or?
Yeah, for sure. Basically, what it comes down to is that our postulate's the best, and it sets up all the rest of your postulates. It just basically states that there's something in existence that we can find and we can observe, which helps us create equations that aren't affected by things such as complex values or anything like that. It still is dependent on time, which is a factor that we have to take into consideration when setting up other equations. But again, it's just one step forward to getting measurable quantities for quantum mechanics, wave functions, and particles in space and time.
Okay, let's thank the speakers. And it is your chance to ask them something. I do have one question.
Yeah.
So you were mentioning, or you wanted to mention, that wave function square is probability.
Mm-hmm.
Then what is wave function when it is not squared? Does it have any meaning?
When it is not squared? the wave function itself would just be like a single value, not of a probability, but it'd be.
Like the graph, the wave function.
Well, you shouldn't
Well, it
be.
wouldn't include complex values or anything like that. So it'd just be, it wouldn't be all the sets or standards of what the entire universe holds.
It is okay to say that wave function itself doesn't have physical meaning, is not related to observable.
True.
You always need to find the expectation value or square.
Right.
And the term for wave function dimension is amplitude of probability, if you want to. More questions to the speakers? If no, let's thank them once again. So, and thanks them for being good in time. So, next team is by Megan Schneider and Luke Lawman for postulate number 2, observables and operators.
Did everyone pick that date, I'm guessing?
Okay, so this is postulate 2. And the definition is for every classical observable, there corresponds a linear Hermitian quantum mechanical operator. So a classical observable is something that you can see with your own eyes or measure yourself in a lab. And examples of a linear operator is any x to the nth power, taking the integration of something or the nth derivative of something. And a Hermitian requires the properties to be real. So an example of an observable is total energy, which has the symbol of capital E, and the operator of the Hamiltonian, which is the negative of Planck's constant squared over 2m, and the square root of the partial derivative plus b. The Hamiltonian we've already seen in the Schrodinger equation. And there are many more examples of operators on the table 4.1 handout, but I'm not going to read them all to you. In the last lecture, we discovered the example of momentum and its operator, which would also fit under this postulate. For a Hermitian operator, the eigenvalues have to be real, but therefore if the eigenvalues are real, it is a Hermitian operator. And then observables have to be real properties that you can measure. So for example, if we take the linear operator, write down the expression in position coordinates x, y, and z, and the linear momentum coordinates of p sub x, p sub y, and p sub z, and replace the coordinates with their operator. So for position in one dimension, our operator symbol is x hat, and what we operate is just multiplying by x. So if you take it and you integrate it a few times and eventually simplify it, you find that x hat equals itself, because x hat is real, and that proves that it is a Hermitian operator. Although there's an important note, the order in which the operator is applied is important. If we have the wave function of sine of x, and we multiply it with p sub x times x hat times sine of x, then we get negative I, the Planck's constant, sine of x plus x cosine x. But if we multiply it in the opposite order, we get negative I Planck's constant x times cosine of x. These are different, although not all Hermitian operators cause it to be different in the order we apply it, but it's important to note that most of them do.
Okay, let's thank the team. And it is your chance to ask something about operators.
Sure.
Questions 1, question 2, I do have. So, try, it is boring just to sit and listen. Design questions while they're speaking. So, can operators exist without wave functions? Do they make sense without wave functions? What are connections? What are at least two connections between operators and wave functions from previous talk? Just try to, any thoughts you have on this subject? Connection, operator to wave function.
The operator is applied to the wave function.
Yes, perfect. It's connection number 1. Good. And any other?
Not
No.
on the
Okay.
spot right now.
So when we will go through the rest of the talks, you will see the main thing, main statement of this set of postulates. So the operator is a bridge between quantum theory and wave function and observable for the real world, what we get on experiment. So first, to change wave function to affect it. Second, bridge to real world. Last chance for the questions. If not, let's thank the team once again. And the next presentation will be, it's my chance to learn your names, by Beth, Podoll, and Aaron Polensky. And they will present postulate number 3. What a good coincidence, it's top number 3. On the measurement.
Alright, so we had postulate number 3, and it just states that any measurement of an observable property A will only yield eigenvalues of the quantum mechanical operator A hat, and any observable property is like any measurement you can actually take and find, so energy, position, momentum, anything like that you can actually measure.
Okay, so the equation that postulate 3 gives us is right here. So it states that the operator is applied to a wave function is the same as a constant times the same wave function, where the constant has to be a real number because, as Megan stated, it has to be an observable property. The set of our wave functions are also called our eigenfunctions of the operator. So that's what is being taken, or the operator is being applied to. And then the set of our constants is our eigenvalues of the operator A.
And then we can only measure values of that property that belong to the set of eigenvalues for that property. And then if the wave function equals some specific eigenvalue, psi equals psi, the wave function and initial, then the only value we can measure is the eigenvalue of the individual eigenfunction.
Yeah, so basically what that's saying is that, so in the previous equation, it was for any set of wave functions. This is saying if we choose a specific wave function, then we can only get the eigenvalue for that specific wave function as opposed to the entire set of eigenvalues. And then down here, it's the final equation for this postulate. It's saying that our wave function can be a linear combination of these eigenfunctions. So it is the sum of all of the eigenfunctions put together into the wave function, where the constant is not equal to 0.
Yeah. Okay, let's thank the speakers from the team. So, what did you want to ask them about measurements, operators, and eigenvalues? Questions 1, questions 2. I do have a couple. If you do not want me to speak, ask your questions. Help your friends. So, you already told it. I would like you to highlight it once again for the class. What is the connection between eigenvalue of operator and results of measurement on experiment? You told it.
Well,
Yeah.
about this. So,
Okay, let me simplify the question.
yeah, I don't know what you're asking.
Would you agree that there is some connection between eigenvalues of operator and results of measurement?
Yes.
Great, nice answer to the question. Okay, so another statement, and they told, they just hesitant right now, that eigenvalues of operators, it is what is being measured in the instruments. That's good. They told it, I believe it. But it will be measurement of this kind only if wave function was prepared in the eigenstate of this operator. But what if a bad guy came and broke the wave function so that it became a wave function in a superposition, as in your last slide. What will be the outcome of the measurement?
It would be just the wave function.
No. In the measurement, you can get only eigenvalue, not the function.
Yep.
So what would you measure?
You would measure only things that would relate to that.
What? Can you repeat?
No.
Okay, let me help them. It is a very provocative, very tricky question that made many people insane in the past. So the statement is postulated, it has not changed. You still will measure one of the eigenvalues. But from time to time, if you repeat experiment, you will measure either one or another eigenvalue. So in average, you need to repeat experiment with this corrupt wave function again and again and make statistics. Do you have objections?
No.
So you sign, you agree with this answer. Thank you much, and thank speakers once again.
I got one more question. I found a question.
Only to the speakers.
Yes.
It's not my time to answer questions.
Okay. So you said that the wave function is a linear combination of the eigenvalue functions, right? Or of the eigenfunctions.
Mhm.
So isn't an eigenfunction just a scalar representation of the same wave function? How do you get a linear combination out of that, or am I misunderstanding something?
So I guess that's, I think if I'm getting your question, that's what that equation was saying. So the operator applied to the wave function is the same as the constant applied to the same wave function.
Gotcha. Cool.
Does that answer
That'll work.
it? Okay.
In some cases, you will be correct. No. Okay. Next presenter,
I'm Landon. Luke is not here.
Landon Johnson. On behalf of Luke, Wiering. Postulate number 4 about expectation values. So it is in very tight relation and connection to previous presentation and my provocative questions.
That's right.
So
So I suppose I should mention what the difference between an expectation value and an average is in quantum mechanics. So in quantum mechanics, when you observe a system, what will happen is you're actually going to disturb the wave function, and whatever it is that you observe, the function will collapse that you keep getting that same value unless you wait for long enough. So what the expectation value is it's more of the average over an ensemble of identically prepared systems, so that you can just basically check the one, check the other, so you don't have to worry about the collapsing wave functions. So it's essentially just an average with a caveat. So I guess this is what the form is. So I took this example from Introduction to Quantum Mechanics by Griffiths. So we're going to let n equal the total number of people in the room. J is the age of whichever person, and n of j will be the number of people in the room that have that particular age j. And if you'd like, you can think of this as like position or anything else that you can represent with a scalar quantity. So the total number of the people in the room, if you sum over every possible value of their age, I should have probably mentioned that we're summing over j here, in all of the sums, I believe.
and some of us are of the age minus infinity.
Well, yeah, I just did it like that just to make it more general. Because if you're thinking about like position or something like that, you know, if you sum over every possible value that there could potentially be, then you'll get the total number of people because, I mean, you've added every person of every possible age or of every particular position. So then the probability of picking someone with a, a given age would be given by the number of people at that particular age divided by, the total number of people. So then if we normalize this probability, we get the constraint that if you sum over every possible outcome, you have a 100% chance of finding somebody of that age because you've looked at everybody. So then if you wanted to find the average value of j, of the age, what that would mean is that you're going to, you'd have to add every single age of everybody in the room. And since you have n of j people of age j, that's just n of j times j for that particular age or position or whatever you want to think about. And then you want to divide that by the total number of things that you counted, and that's just the average. And so if you look at that, that is actually just j times the probability of j. So then if you were to look at something like the average age squared or some sort of function of it, you would put in the age squared times the probability of finding the particular age without squaring the actual age itself inside of the probability, because that ends up meaning nothing if you do that. So generally speaking, the average value of any function of whatever it is that you're looking at will be that function times the probability of that particular value. So if we take this from the discrete case to the continuous case and let the difference between each value shrink to nothing, then you end up getting an integral, and you have the same arguments there. Yes, I think that would still be j. So with a wave function, if you were to try to find a particle between some positions a and b, the integral of the wave function squared will give you that probability. And again, we have the normalization constraint that if you look over everywhere that the particle could possibly be, it's going to have to be somewhere, so you're going to find it. So the expectation value of like a position, let's say, of a wave function would be the integral over all possible space times the value of the thing that you're looking for and the probability of finding it at that particular place. So then if we generalize that to any sort of observable that we can think of, this is basically a function of x or something else if you'd like, then we just have to sandwich that operator in between the two wave functions. And the only real justification that I can come up with for that is that these wave functions are vectors, and this is a matrix. This is a column vector, and this is a row vector. So if you were to pull the operator out from here, then that would not make any mathematical sense anymore. I can't really come up with a physical interpretation of why it has to be in the middle. And then if you were to look at anything in 3 dimensions instead of a 1-dimensional space, you just need to integrate over all space instead of just the 1 dimension. And that's it.
Okay, let's thank the speaker. And give us a chance to ask questions. Questions 1. Question, please.
How do you get so good at explaining things, man? That was awesome.
I
really have
well, I've taken quantum mechanics 1 and 2, and I'm a math and physics major, so I've done functional analysis too, which explained all the things that made no sense to me at all when I took quantum, like why you can do the things that you do. So I have a little bit of experience with this stuff.
Well, that was my zero question.
More questions or more excited comments? So, what's the difference between the statistical average and quantum mechanical expectation value? It is a provocative question.
The statistical average would be the average over one particular system, and the quantum mechanical expectation value is it would be that average value but taken across many different systems that are all identically.
Would you already decide and agree with me that it is opposite?
What then?
Would you agree that it is opposite? Statistical is over many systems and quantum mechanical is over one?
I guess when I took quantum mechanics, and the way that Griffiths explains it in his book is that the expectation value should be interpreted as...
Then you should open discussion and start arguing. So there is a big counterintuitive component in quantum theory, and what London has presented is an attempt to bring quantum mechanics to our intuitive understanding about people in the room with different ages. But it is an attempt to speak about several systems, an ensemble, which is a statistical physics or mechanics. But quantum theory would work even for isolated systems. So in order to expand your explanation to truly counterintuitive quantum system, we should pick up a person who is in a superposition of like age being 23 and 24 years old. Maybe it's a very poor connection, but maybe a person at the midnight before the birthday, when he doesn't know or she doesn't know how old he or she is. So results of measurement can give both either this or this value. So it is a big difference between statistical average and quantum theory. But the mathematical part, what you presented, was absolutely correct. Just interpretation was a help us to connect counterintuitive to simple things. Want to argue? Back?
I wouldn't argue against
Good.
that. I guess,
Then we'll continue discussion later. More questions? If no, let's thank the speaker and continue our intense schedule with Christian Nilles and Rennon Thorton. Postulate number 5 about how the observer changes the system.
Yes, I know I said my name only. He's also part of the group.
So we had postulate number 5.
Yes.
The main thing we took from this is by measuring or observing a system, you can effectively alter it. Crude analogy I liked was checking like your pressure in a tire. You get your reading, but in doing so you let some of that air out, so you've affected the state of that. Now in physics this is known as the observer effect. In a lot of the situations it's negligible and doesn't need to be accounted for, but when on a quantum scale you need to account for that, and it can be substantial. This idea is kind of explained in the thought experiment of Schrodinger's cat, and was even studied in an experiment done at the Wiseman Institute.
So going off what he said, the thought experiment that probably all of us know is the Schrodinger's cat thought experiment. Schrodinger, the way of explaining this, decided to put in his thought experiment a cat into a box. In this box, there's a vial of poison that at some random moment in time, we don't know because you close the box, the vial will open and kill the cat. Well, because the box is closed and we cannot see the cat is both alive and dead at the same time. So, now the question is how is this similar to electrons in the fact that it is both a wave and a particle at the same time? So then we have the Wiseman experiment that goes through and does this experimentally in real life. What the institute did is that they took a current and ran it through a double slit, and on this double slit area they put some type of device that was able to observe what is going on. Now, when they started observing, the current going through did not. The more they observed, the less interference that was happening, and it ended up forming into particles. As you can see right here, as the more observance increases, the more that happens. But as they decreased the device observing the current, you see interference growing, showing that as you observe, it becomes more of a wave than a particle.
So like looking at the Wiseman experiment, if you're wanting to observe the system electron when it's acting as a wave, after observing it, you force it to act as a particle. So if you're doing measurements after that, it's a different state. So to get back to the wave, you're going to need to manipulate it back to the original system to do your measurements. And that was a thing, but when you're doing subsequent measurements, you need to make sure that you manipulate the system back to its original state.
Okay, thanks the team. And it is time for questions or comments or expressions of happiness. I have an expression of happiness. They really very comprehensive. I learned a lot. So, and it is good pedagogical step to say that first for interference, for superposition, you look on the wave nature, but at the measurement, you look on it as a particle nature, and you observe this change of the state, right? Mm-hmm. I cannot design question, I cannot comment. So, in previous talks, maybe in number 1, last slide in number 1 was a superposition. Summation, eigenfunctions with different expansion coefficients. So, the measurement breaks superposition and projects system onto one of the eigenstates. So it is, I was trying to say what they were telling in more standard way. But they did in a very nice illustrative way. Last chance for other questions. If not, let's thank the team once again. We are a little behind schedule, but we still have chances to finish in time. Postulate number 6 by Andrew Olsen and Braden White. Or Wait, like heavyweight. Okay. So something about time dependence.
Alright, so we got postulate number 6, which is kind of generally stated as the time-dependent Schrodinger wave equation, which is kind of a general thing. So what we wanted to do is give a better interpretation of maybe a solution or the different parts that would make up the time-dependent wave equation. So we kind of did this first slide kind of in class the other day. You have your time-dependent wave equation on the top, which would be a linear first order partial differential equation. And then you can make some substitutions, assuming that the time portion is independent of the spatial coordinate portions. And you can guess the solution to be something as such. And you can reduce it then to a linear second order ordinary differential equation, which is much simpler to solve, especially in relatively easy cases.
Alright, so what we're going to get into is what is H hat. It's essentially the sum of the kinetic and potential energy, T being the kinetic and V being the potential. So T is generally similar across all systems, so it's given by that equation. V, however, differs in like big situations. For classical, we have gravity, the standard gravity equation, and the spring equation. And then quantum, we have a slightly different equation. I'm gonna get into that a little bit.
Well, so gravity, we all know MGH, right? Just an example of a potential that we all know. But more specifically, we can talk about the spring, right? So it has this effective rigidity, constant K, you can call it. And if you remember what that is, K is equivalent to the square root, or it's related to the frequency of the oscillation between the spring, right, and the mass. So it's actually equivalent to, say, K and omega squared if you make the substitutions for mass as well. So we write it this way because in quantum mechanics we look at more of the wave-like nature rather than the simple rigidity. And that happens in a lot of the potentials that we look at. And to tie this all back into the time-dependent equation, you can solve these using the potential V and the potential T as that the second order ordinary differential equation. And so then the time portion just comes in at the end as that exponential factor relating the energy, which is encapsulated within that lambda I've shown. That's pretty much.
Okay, let's thank Braden and Andrew. I promise to learn all names by the end of the semester. So, questions? I definitely have some. So, in the previous slide, last equation to the left.
The EX.
Yes. How general it is. So, let me prepare a question and I will declare what I mean. We are trying to stay away from practical applications for a couple of meetings and try to declare very general statements that will work for universally for any system. And I have a suspicion that first two lines are general, but here, instead of using Hamiltonian operator, Braden and Andrew replaced it by the second derivative. And the suspicion is that maybe it's not general enough and it deals only with one particular case study?
The free electron
Where?
vacuum.
Yes. So everyone, if you do not see sparks in the eyes, you need to repeat it in different words.
So the way this is written, to make it more general, to incorporate any general potential, like I did on the following, where I took different arguments of V, I simplified it. There should be a dx squared here in parentheses, along with some arbitrary potential operator with a coefficient in front of it, because I created this E argument, so it should be the second derivative plus some coefficient, which would be similar to E minus the eigenvalue.
Okay. So, but it's still with this generalization, it will be their conclusion that it will be linear second order equation is correct. One more question, if no other questions. Would you agree that this equation can be characterized as eigenvalue problem? Good, thank you. Nice. Let's thank you. So, and we have last but not least presentation by Jan Bergh and Mark Almlie. So we are done with postulates of quantum mechanics, but we need to refresh. You can come up and set up your slides. But after we agree with these background postulates and before we go to applications, we need to be sure that we have enough mathematical muscles. And you have observed from the slides, for example, from last slide, last equation, that we need to solve eigenvalue problem. And from the first and second postulates and answers on the question that from time to time, we need to apply operator to the wave function. Two procedures, eigenvalue problem and apply operator to a function. This is very closely related to our Babbage from the taken, not only calculus, but also linear algebra. And these two operators, multiplying operator by a wave function, which is translated into matrix by vector, and then the eigenvalue problem will be illustrated by Jan and Mark. The floor is yours.
Before we get into the actual eigenvalue stuff, multiplying two vectors together, we have the cross product, which is done by taking the one of the rows and then multiplying it by the square that's left over if you eliminate an item's row and column. And then you take the determinant of that leftover square, and then so you get I plus I times BF minus C, and you take that for I and J and K, and you get your cross product.
Can you ask the class if everyone is happy with concept of determinant?
Does everyone understand the determinant? It's kind of what I was trying to explain. So the determinant is for 2 by 2, you multiply the BF and then you subtract the EC. And then so with a 3 by 3 determinant, you can take the top row, so the I times the determinant for the bottom right hand corner, and then for J you would take AF minus DC, and then K you would take AE minus DB over here, and that would give you a vector as a result. So that's everyone gets that. And then skip over diagonalization because he'll actually cover that with what we actually care about. And then for multiplying matrices, I actually didn't get this slide in on time for the handout. But the slide before it for multiplying matrices can still be applied. You need a 1x3, so rows by columns, and then you need to have the columns of the first one times the rows of the second one match up. And then so you can multiply by the first row by the first column, and then the second row by the second column. However, what we're concerned with is multiplying vectors. This would also be called the dot product. You just multiply them in a row and you get a scalar result, or a 1x1 matrix. And then that's all I've got.
Okay. And I'm not super fancy, I don't know how to work computers, so I just wrote things, so I'm gonna point up. So, eigenvalues, basically how you determine your eigenvalues from your operators is you want to take the determinant of your operator and set it equal to 0, right? So it's your determinant of actually your eigenvalue times the identity matrix, right? Minus your operator, set that equal to 0, if that's what this is. So that's your eigenvalue times your, keep forgetting what that's called, identity matrix. It's that one. Minus a equals 0. So then your determinant would end up being lambda minus a times b, and then b, c, lambda minus b. So then your determinant is going to come out to be a quadratic equation for the 2x2 matrices, right? And you just solve for your eigenvalues, and that's how you end up with your eigenvalues. I don't have anything written for eigenvectors, but basically, can I write on this? No, I can't. Okay.
You should be able. You should be able. Let's try.
Oh, bottom left. Oh, nice. Yeah.
Yeah. Point. Select this pen when it pops up.
Okay. Nope.
No, when it pops up, you need to select the pen.
Which pen? There's 2 of them.
This one. Select.
Oh, see, that makes a lot of sense. Thank you. Okay. So then for an eigenvector, basically we just found the eigenvalue. It's right here. So for the eigenvector, if you want to find that, it's basically you take your, I'm just going like this. A times lambda equals your lambda v, right? So you're trying to find your vector right here. Then you would plug in your eigenvalue and multiply that by your vector, and then you kind of work it through.
You want AV times lambda v, right?
Good.
Oh, thank you. AV times lambda v. Get rid of that. That makes more sense. So then you take your eigenvalue down here and then multiply that by your vector, so you can just put that into your v over here and then multiply it through.
Okay, and solve that system of linear equations.
Yes. So then I can't see my thing. So you would end up writing out your a and then solving for your v. If your v is v1, v2 equals these. So like your a's. So you would write out this system of linear equations and then put your value for lambda that you found into your v over here. Right?
Keep going. We are short in time.
Well, I think that's all I had.
Okay, let's thank the speakers. And the questions to the speakers. To Jan and Mark. I was not looking into the class and I didn't notice were there sparks in the eyes by the word of determinant. So therefore, can you guys tell what is determinant and who needs it? Give a definition, not mathematical definition, but for like common citizen.
Well, the determinant is the, isn't it like a matrix times No, it's not a matrix times a null space, but a determinant is.
It is a procedure that converts matrix into one number.
Okay, that works.
Objections? Okay, and there are some specific rules how to make it. Even without this diagonalization and eigenvalues, it is a way to judge if a matrix is a good matrix or bad matrix. Some of you, I mean you too. So this gentleman were offering pseudo diagonalization, simplified diagonalization by swapping rows and columns. But such tricks work only if the determinant is not equal to 0. So if the matrix is non-singular. So determinant is quality control of a matrix.
If it's invertible, you can do that.
Yep. And in the advanced chapters of linear algebra, one uses it for finding these eigenvalues. It is a background from linear algebra that we definitely will be using in the course. So ask them now after the class, refresh your memories about diagonalization. It is something that you will definitely need. Let's thank speakers once again. Many thanks to all presenters. And from now on, you are certified experts in postulates and quantum mechanics. Looking forward to see you Monday 11 at this place this time. And we will go to the labs and homework starting next week.